Hello, so welcome to my video on differentiability. Today we're going to explore the relationship between differentiability and continuity. So let's begin with the definition of differentiability. We say that a function is differentiable at a point A if f prime of A exists. So recall in a previous video we saw the definition of f prime of A, the limit definition of a derivative, which is limit as h approaches 0 of f of A plus h minus f of A, all that divided by h, or the equivalent definition, the limit as x approaches A, f of x minus f of A divided by x minus A. So if this limit exists at a given point, we say that the function is differentiable at A. Our second definition is differentiability on the interval. So a function is differentiable on an interval AB if f prime of x exists for all the x's in that open interval. So note that the open interval can be from let's say negative infinity to positive infinity, so we can include infinites as well. So we have differentiability on an interval if it's differentiable at each point in that open interval. Okay, so let's look at a theorem now. So in this very important theorem, it states that if f of x is differentiable at A, then f of x is continuous at A. So essentially what it's saying that differentiability implies continuity. Okay, this is a theorem. Let's go ahead and prove it. So proof. So the issues with proof is knowing how to start. There's no systematic way to prove a statement. You're essentially just trying to build from what you know and obtain the conclusion. So we know that f of x is differentiable. That's information that's given. We're allowed to use that. So we know that f of x is differentiable, meaning that we could use the fact that f prime of x exists. So we have this. We have f prime of x is equal to the limit as h goes to 0 of f of x plus h minus f of x over h. We have this information. We know this limit exists. Or similarly, we could use the fact that limit as x approaches a of f of x minus f of a over x minus a exists. So this is information that we know. What do we want to show? We want to show that f of x is continuous. Well, what's the definition of continuity? So what we want to show is that the limit as x approaches a of f of x is equal to f of a. This is our goal. So we want to show this. We want to show that the limit as x approaches a of f of x equals f of a. So here you have to ask yourself, which formula are you leaning towards using for differentiability? Should we use this one over here or this one over here? So the one that I would probably use is the one where the limits are the same. Here we have the limit as x approaches a, so I'm leaning towards this one here. Okay, so we're gonna build from this and work our way to get this conclusion. That's our goal for this proof. Okay, so so the starting point is a bit arbitrary, but I could state that f of x, so this is just like stuff that you put on the side. It's not part of the proof. You're kind of just brainstorming at this stage. So we could start off with the fact that f of x minus f of a. So ideally when you're taking the limit as x approaches a of f of x and that's equal to f of a, what you also want to do, or another way of thinking of it, is the difference between f of x and f of a when you take the limit as x approaches a is small. You can think of it as this way. So I'm starting off by taking the difference between f of x and f of a. Okay, and I'm trying to build towards this thing. Okay, so how could I get from this, what I just started with f of x minus f of a and build towards this, is that I'm missing x minus a on the denominator. So what I could do is take f of x minus f of a, that's the same statement. This is obviously equal to this, and I want to divide it by x minus a to get this. But you can't just divide by some value. It's a fancy way of multiplying by 1. We're going to multiply the top and the bottom, the numerator and the denominator, by x minus a. So now this is an equivalent statement because x minus a divided by x minus a cancels, and this is the same. So far so good. So what we did is we constructed this, and this is similar to this, what we have here. The only thing that's missing now is the limit. So one of the properties of limits that we saw in a previous video is that you could take the limit on both sides of the equations because it's equal. We'll take the limits on both sides of this equation, and here we have a multiplication. And one of our properties states that if you have a product, you could take the limit of each term individually. Okay. So if I put the limit in the front of this side, limit as x approaches a, on the left side of f of x minus f of a, this is equal to the limit as x approaches a of f of x minus f of a, all this divided by x minus a, times the limit as x approaches a of x minus a. Okay. So the limit of this difference is equal to the limit of f of x minus f of a over x minus a times the limit as x approaches a of x minus a. And what you have to catch is that this piece here, let's put in a square bracket, is our definition of a limit. Sorry, it's the limit definition of a derivative. So at this stage here, what we could do is call this thing here f prime of x. And the piece that's sticking out over here, what we can do is evaluate the limit. If we replace the limit x with a using direct substitution method, a minus a is 0. So you have f prime of x times 0, which is ultimately equal to 0. Okay. So remember, this is our goal. We want to show this. How does this statement here equal to 0 help us find this? So let's make some room. Let me continue up here. So we used our definition of the fact that f of x is differentiable at this stage here. And now let's go and complete the proof. Again, we want this. So we could start off with the limit as x approaches a. So limit as x approaches a of f of x. And we could use this clever technique to show that this, how could I write this, is equal to the limit as x approaches a of f of a plus f of x minus f of a. Okay. So this is a fancy statement of essentially what some teachers call garbage in, garbage out. It's a fancy way of adding nothing. What we did is we took this statement here, we added in an f of a, but at the same time we're subtracting an f of a. So if you remove this term here, the f minus a, and the f of a and the negative f of a, because f of a minus f of a is 0, this is the same statement. So we have the limit as x approaches a of f of x, and we're just adding something and subtracting it. It's a fancy way of adding nothing. Okay. Right, and at this stage here, again, same property. If we have the limit of multiple terms, you could take the limit of each term. So what we can do is take the limit of the f of a in the front here, plus take the limit as x approaches a of this whole thing here. Let's put this in brackets. F of x minus f of a. And what we showed down here is that the limit as x approaches a of f of x minus f of a, this piece here, this whole thing is equal to 0. That's what we showed down here. This whole thing here is equal to 0. So now that this is gone, what we have here is the limit as x approaches a of f of a, but the x tends to a. We don't have any x's here. So this is the identity property, so this is just equal to f of a. And we showed that the limit as x approaches a of f of x, which is what we have here on the left side, is equal to our f of a. Therefore, we have continuity. Differentiability implies continuity. And this is the proof. Very important theorem. We like functions which are continuous and which are differentiable. So if we have differentiable functions, then we have functions which are continuous. Okay. This is the proof. Let's go ahead and think about an equivalent statement. So this is done. I'm going to erase. it's always a good idea whenever you're giving a statement, this is called the direct statement, to look at what's known as the contrapositive and the converse statement. So let's look at those. This is the direct statement. So direct, we could think of it as P implies Q. Okay, this is your first statement, which is if f of x is differentiable, so differentiability implies our conclusion was continuity. P implies Q. A very good strategy, especially when you're doing proofs, is to look at what's called the contrapositive of the statement. Okay. The contrapositive of the statement is if the original statement is P implies Q, the contrapositive is not Q, so that's a negation symbol, implies not P. So the negation of Q. If f of x is continuous at A, that's your Q statement. Let's put a Q over here. And f of x is differentiable, so differentiability at a point. This is P. Not Q would be f of x is not continuous. So the contrapositive of this direct statement would be if f of x is not continuous, then f of x is not this implies that not P, the negation of P. P is f of x is differentiable, so f of x is not differentiable at a point A. So f of x, if we don't have continuity, then we don't have differentiability. So this contrapositive is an equivalent statement to the original. These are equivalent statements. They're both, in this case, true. Okay. And another important statement to always look at is the converse of the statement. Okay. The converse of the statement is if the direct statement is P implies Q, in this case differentiability implies continuity, the converse is the opposite, Q implies P. So we're just reversing the order. So if f of x is continuous, does this imply, we don't know, that f of x is differentiable? So if f of x is continuous, do we have differentiability? We're looking at the opposite, the converse of the statement. Okay, so I'll let you think about this, and we're going to answer it in just a few moments. Okay, so if the function is continuous, try to think if we have differentiability. Okay, so now let's look at the cases where we don't have differentiability. So here we look at the three cases of non-differentiability. The first case that we have is when we're given a corner or a curb. Okay. If the function that's given has a corner or a curb, let's sketch it out, then the function is not differentiable. We cannot take the derivative of this function. Okay, so let me draw the function in green. So something that looks like this. Okay, let's say a shark fin. Why is this not differentiable? So as you can see at this value here, I'm going to draw it in red, this tip, we have a corner point. We saw in a previous video that in order to have differentiability, we associated it to a rate of change. We looked at the limit definition of a derivative and showed that that's equivalent to the slope of a tangent line at a given point. So if this is the point A, let me do it in red. If this is the point A, do we have a tangent line here? Oh yeah, we do. I could draw some line like this. Okay, but we need one single tangent line. In this case here, we don't have one single tangent. We have many potential tangent lines. Because notice that the line that I drew here goes through hits the function at exactly that point. But at this point, notice that you could have multiple tangents. This line that I just drew again hits the function at only that point. And I could draw this line here as well. Okay. So because at this corner of this curve we could have multiple tangent lines, it's not differentiable. Okay. Let's look at the second condition, discontinuity. If the function is discontinuous, then it's not differentiable. This came from the contrapositive of the statement that we just proved, of the theorem that we saw earlier. So the contrapositive said if it's not continuous, then it's not differentiable. Let's look at an example. This is y, this is x. Let me draw the function in green. So let's say, I don't know, we have something like this at 2, and then at 1, it's an open dot, and it continues like this. Okay, so we have sort of like a step function, and this continues forever, this continues forever. Why is this not differentiable? Well, if we look at this point here, the solid dot, we'll call this A. Again, we run into a similar problem here where we could have multiple tangent lines hitting just that endpoint. Okay, so we run across a similar issue where we'll have multiple tangent lines at that given point. So we don't have differentiability. Okay, so differentiability here fails in both these examples. The last case that we have is vertical tangent. So let's take a sketch. This one, so with discontinuity and then vertical tangent. Let's draw the function in green. This is y, x. So if the function looks something like, I don't know, something like this. If we focus on this point here, call this A, notice that the tangent line at this point here is going to be a vertical line. Okay, it's poorly drawn, but it's, imagine just a straight line that hits the function at just the red point, and it's completely vertical. This gives us a vertical tangent. This is not possible. Your slope can't be infinity. So this is another case where differentiability does not work. Okay, so earlier I asked, looking at the converse statement, does continuity imply differentiability? We saw that the contrapositive of the statement was equivalent to the original statement, but what about the converse? Does continuity imply differentiability? So by now we should probably be able to see that this is false. Okay, this is not true. And we have an example here just on the board. This function here is continuous. Yet, because it has a corner or a curve, it's not differentiable. So the converse statement is actually false. This continuity implied differentiably, that's false. Another typical example, which is one that I constantly refer to, is I consider the function f of x equals absolute value of x. This is a function in which the absolute value we cannot take the derivative of. Why not? If we sketch this, let me just erase the board and give it a quick sketch. Okay, let me extend it. This is the x-axis, this is the y-axis. Let's draw it in green. F of x equals absolute value of x. Looks like a V going through the origin. Okay. And this is not differentiable because at the vertex here, the lowest point, we have a corner which could have multiple. So this is our counterexample. We could have multiple tangent lines. So f of x equal to the absolute value of x is a continuous function. I could trace this without lifting my finger, yet it's not differentiable because we have a corner. So this converse statement is false. Okay. So this is a counterexample. So when you're proving a statement, you have to provide an entire argument. But when you're disproving an argument, it's sufficient to provide just one counterexample and to disprove the claim. Okay. Don't prove a statement with one example that does not work.